welcome to True Projects. In this video, we are going to explain about the project which is YOLO, an efficient detection algorithm for insulator defects in complex backgrounds of transmission lines. Before getting into the project, first let us understand what is the project about. So, the power industry it relies on the transmission lines to deliver energy consistently, and insulators are key components that prevent electrical leakage. However, this leakage, that is, these insulators are constantly exposed to outdoor elements which can lead to defects like cracks and contamination. If these issues aren't identified quickly, they can disrupt the stability of the power grid and result in failures. For instance, during storms, rain can carry dirt and debris that may contaminate insulators. Such contamination can lead to power outages or even dangerous situations like electrical fires. Traditional methods, that is, traditional manual inspections, have been used to detect these defects, but they can be slow, costly, and prone to human error. That is where there is a pressing need for automated detection solutions which can identify issues more efficiently and help maintaining the safety and reliability of our power system. With the advancements in the deep learning, we are moving from manual inspections to using the object detection algorithms like YOLO, which can quickly and reliably identify defects in the power systems. For example, detecting a faulty insulator promptly can prevent major outages and safety issues. But but there are challenges remaining. Detecting defects in complex environments where backgrounds can be cluttered is difficult. There are also multiple fault types that can occur at once, complicating accurate identification. Moreover, many high accuracy models are too large for real time deployment on smaller edge devices, which are essential for immediate monitoring. So, this project aims to develop a solution that is both accurate and lightweight, making it practical for real time use in the field. By tackling these challenges, we can significantly enhance the safety and reliability of our power infrastructure. So, in this project, we are introducing an insulator lack you only look once model, that is YOLO algorithm. It is specifically designed to tackle some of the common issues we face with the current insulator defect detection models, especially when we are dealing with the complex backgrounds or multiple targets at the same time. So, in this IL YOLO is built on the YOLO V5 framework, which is already a solid foundation for the object detection. What sets is apart are three enhanced modules we have integrated into this design. So the first one is Insulator Lag Global Attention Mechanism, that is ILGAM for short. This module is crucial because it helps addressing the problems like weight interference and also the loss of important information during the feature extraction process. As a result, it significantly boosts the model's ability to accurately detect defects even in complicated environments where the background can be quite busy or cluttered. Coming to the second module, that is Insulator Lag 3, that is ILC3. This is one it is a really important because it helps us to focus on critical information while also improving how we extract and combine features from the data. What this means is that significantly reduces the chance of false detections and missed defects, which is crucial when we are trying to maintain integrity of our power infrastructure. Moving on, we also have the insulator lag SPPFCSPC. So this module takes it a step further by enhancing the extraction of features at multiple scales. It does this by effectively balancing our attention between the key details and the broader context of the images we are analyzing. This balance is essential for detecting and classifying various defects, especially in complicated backgrounds where multiple issues might be present. Moving on to further improve the performance, in this project, we are implementing advanced versions of the YOLO, that are YOLO V5X6 and also the latest versions which are YOLO V8 and YOLO V9. These iterations bring significant improvements in analyzing images and also detecting defects more accurately. They are more efficient and reliable, which helps us better tackle the challenges we have been facing with the defect detection. On top of that, we have built front end using Flask framework. So this allows users to interact with the system more easily. We also made sure to include authentication features to keep things secure. This means that only authorized users can access and test the system, ensuring that our data remains protected while providing a seamless user experience. Moving on to the implementation of the project, first, we start by importing the required necessary packages and the libraries needed for our project. And then we explore the data set. So here we will be we will be reading the images. That means we will be working with them and plotting them. And it helps us to understand what kind of data that we have and its characteristics. And then we do image processing where we convert images into a blob object. This format simplifies its data structure for our model to understand. And then we define bounding boxes. That is, here we define the classes of the objects we want to detect, specifically the insulators. Then we declare bounding boxes around the objects of interest in the image, making where the defects are located. Then finally, we convert images into NumPy array, which allows for easier data manipulation. Next, we load the pre-trained models. So we load the pre-trained models by reading the network layers and extracting the output layers that we will use for detection. And then we are supposed to do some image processing where first we will be appending the image annotation files to our images to provide additional context. And then since different libraries uses different color formats, so we will be converting images from BGR to RGB. BGR is nothing but blue, green, and red, and RGB is nothing but red, green, and blue. So we will be converting images from BGR to RGB. Then we create a mask for better segmentation, which helps isolate the defects from background. Then we resize the images to fit the input requirements of our model. And then we do the data augmentation. In this step, we apply some augmentation techniques, which is randomizing the image. So we randomize the images to create variations. And we rotate images to help the model learn from different angles. And we transform additional transformations, ensuring the model sees a diverse set of images. And we process the data according to the specifications of the YOLO family, ensuring it's structured correctly for our model. At this point, we will be building the model, defining its structure and parameters to align with the detection needs. Then, we train the model using the prepared dataset. This is where the model learns to recognize the defects through a learning process. After training, we will be dumping the model, which means that after training, we will save the best performing model for future use in detecting defects in the new images. So, we will be dumping the model. That means we will be saving the best performing model. And we create the front end of our application using Flash framework, setting up user registration and login features with an SQLite database for secure data storage. And users, they will be uploading images to the system for defect detection. Once the image is uploaded, that will be pre-processed. That means we will pre-process it in the backend to prepare it for defect detection. And we utilize the train model to detect the defects in the uploaded image. And the final outcome will be displayed to the front end in the front end, informing users of an identified defects on the insulators. So this is how we implement the project. Coming to the algorithms used, these are the algorithms used in the project. So this is the proposed model and these three are the extensions. Among all the models evaluated, we found that YOLO V9 has the outstanding performance among all the algorithms that we have built. Moving on to the requirements of the project, we need basic requirements to implement the project. Coming to hardware requirements, we need operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Coming to software requirements, we need application of Anaconda, primary language of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, and front-end technologies are HTML, CSS, JavaScript, and Bootstrap 4. Now let us execute. To execute, open the code folder of the project. So these are the source code files in the code folder of a project. Let us understand each of them. How will they be used in the project? So coming to static folder, in this folder we have files related to CSS, JavaScript, and Bootstrap files. These are important for the visual appeal of the project. Coming to templates folder, this folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. And this is the app.py file. This .py file contains the information related to front-end logic of the project. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. And here we have some model files. So this is the model file which contain the algorithm information and that will be loaded into the project code during runtime of the application. And here we have notebook file. It's a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. And here we have signup.db file. This file is a database file which is used to store the user information. And here we have some folders in the starting. So in these folders, we have the data set. So coming to this YOLO V6 folder, in this folder, we have two subfolders. One is images and the other one is labels. Let's open the images folder. Here we have two subfolders. One is train and the other one is valid. In train folder, we have the 700 in total 734 images. These images are used to train the models to detect the insulators and also the lags in it. And here in the validation folder, we have the images that will be used to test the models. So we will be using train to train the models, validation images to test the models. Get back. Coming to this labels folder here, in this folder, we have the files that containing the annotations or the labels for the objects in the corresponding images. So here, each label file corresponds to an image file in the image folder, providing the details about object locations and the classes within the image. For example, this annotation file, it corresponds to this image in the images folder. Similarly, for this particular image, we have corresponding annotation file in the train folder. Accordingly, we will be also having in the validation folder. So here, these label files, they follow the YOLO format where each line represents a detected objects. So let's open a file for sample. Here, each line represents a detected object. Each line specifies the object's class index. So this is the object class index, which is followed by its bounding box coordinates. This is the height, this is the width, this is the limit, and this is the Y limit. So these are the bounding box coordinates normalized to image dimensions. Let's close this. Similarly, we will be having in the other files also. So now get back to the main code folder. Similarly, we will be having in the YOLO V4, YOLO V5, YOLO V7, YOLO V8, YOLO V9, we'll be having the images and the label files. And these each folder contains the same images, but they are annotated differently because each YOLO version requires its own specific type of image annotations for training and testing the models effectively. Having separate folders helps keeping the dataset organized, ensuring that each YOLO version receives the correct annotations it needs to function properly. So this is all about the code folder. Now to execute, copy the code folder's path. So copy the code folder's path from the address bar of the file explorer. So I'm copying the path. Now open the Anaconda prompt. So it is open using the command cd followed by the space, paste the copied path and now click on enter. Here, if you observe, current directory is changed to the code folder's path. Now compile the app.py file. So give the command python space app.py and click on enter. This command, it will execute the Python script and perform runtime check in syntax and check for the logical errors. After running the app.py file, Flask framework will host the application at the local address, which is the local host and the port unless configured differently. So this is the local host and this is the port. And now we have to copy this local link provided by the Flask framework and paste it in any web browser. So I'm copying the link. I prefer Google Chrome, so I will paste it in that. Paste the link here. At the end, click on enter. This is the web page of the project, which is displayed in the browser, and this is developed using Flask framework. So we need to register first. Click on register and enter all the registration details if you are registering newly. I have already registered, so I'll directly log in. Click on login. Provide your username and the password. Click on login. We have logged in successfully and we are redirected to detection page of the project. So here you can see a choose file button, right? We need to click on that for uploading the insulator images. So here, click on choose file. Let's open the sample folder in which we have test cases. So these are the test cases. We will be using them to detect the insulators and the lags. So let's open the first image. Click on open. Here it is loaded. Now let's click on upload. And here we got the two detections. One is insulator and the other one is lag. If you observe, insulator is drawn in the red color bounding box. It is detected in the red color bounding box. And with the label insulator with the 0.85 confidence level. That means it shows the accuracy of the model, that is how accurately it is detecting that particular insulator object. And here there is a lag in it. So here if you observe, it is detected in the yellow color bounding box, and that is labeled as lag, and it has 0.80 confidence level. That is how accurate in detecting this lag object. Let's get back and try using some more objects. Click on detection, click on choose file. Let's try with this image. Click on open, click on upload. And here we got the detection. So insulator has been detected and also the lag is detected. Insulator is detected with the 0.88 confidence level, that is confidence score, and lag is detected with the 0.77 confidence level. Now get back, click on detection, click on choose file. So let's try with this image. So here also we got the two detections. One is the insulator and the other one is lag for the 0.89 and 0.82 confidence levels accordingly. Get back, click on choose file. Let's upload this image. Click on open, click on upload. And here if you observe, there are two insulators detected. One is with the 0.77 probability score, that is the confidence level, and the other one is with the 0.88 probability score. And here no lag is detected. That means there is no defect in the insulators. Let's get back. Click on choose file. Let's try with this image. So here there is lag. That means there is a defect in the insulator and both of them are detected. Get back. So let's try uploading this image. Click on open and upload it. So here we have detection that insulator is defective. So that is why there are two detections. One is insulator is detected and the other one is lag. That means defect in the insulator is detected. Let's try using some more images. Let us upload this image. So here we have the detection that there is defect in the insulator, where it detects insulator and the defect, that is lag in it. Let us upload last image. Click on choose file. So let's upload this image. So here also there is a defect in the insulator. So here we have the detection. Now get back. This is how we need to upload the images. Based on the uploaded image of the insulator, we will get the detection whether the insulator is defective or not by using the YOLO models. Now let's check with the graphs. So click on graph. So here we have precision recall graph of YOLO model. So here blue color represents the insulator, navy blue represents all classes, and orange represents the lag, that is the defect. And here we have FN score graph of YOLO model. Here we have the confusion matrix. And this is the precision comparison graph. This is the recall comparison graph. And this is the mean average precision comparison graphs. So these are the metrics used to evaluate all the detection models. Now click on log out. In this way, by using the YOLO models, we will be able to accurately detect the defects in the insulators. So this is all about the project.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.